Welcome back to Multivariate Calculus. In this video, we're going to be studying limits and continuity for functions of several variables. Just like we did when we started studying vector-valued functions, we're going to take our inspiration from the definitions of limits and continuity that we learned for functions of single variables. So without further ado, let me get my head out of the way and let's jump right into that. So for a function which maps from the real numbers to the real numbers, the function of a single variable that you learned about in first semester calculus, we can say that the limit as x approaches c of f of x is equal to L if and only if, for any value of epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of f of x minus L is less than epsilon whenever 0 is less than the absolute value of x minus c is less than delta. All right, that's the classic definition of the limit that you learned about in calculus. And the picture there, we are generally looking at a function that does something kind of like this, and we're looking at our point in question, which is c. We're looking at our y value, which is L. And we're picking some window, epsilon, above and below the value of L. And we're using that to set a window of delta to the left and to the right of c. And the claim is that we can always, if the limit exists, find a way to devise this box so that the function exits through the left and right of the box, not through the top or the bottom. In a function of several variables, that can get to be a little bit tricky. So let's start by thinking about what the picture is going to look like, and then see if we can figure out what the definition should look like from there. All right, so if we've got a surface that's going on and doing its thing, and we don't really have just a single letter to use here for C, we need two variables. I'm going to go ahead and call it x naught, y naught. But we can still move up from that and find our value of L. But the real trick of all of this is that I'm no longer bounded in how I can shift away from x naught, y naught. I can move away from it in the x direction, in the y direction, or anywhere in between. Right? To handle that, what we're going to look at is, we call it a delta ball. For a function of two variables, it's a circle of radius delta. If you have functions of 3 or 4 or 7 variables, it will become a sphere or a hypersphere or whatever dimension you need. We're going to stick with two variables because it's pictures we can actually draw, but this does extend out, and that's something that I want to make sure that I mention several times. All right, so we have this circle of radius delta, and we want the distance from our point x naught, y naught to fall somewhere inside this circle. So using the distance formula, distance is given as the square root of x minus x naught squared plus y minus y naught squared. And we want that distance to fall somewhere between 0 and delta. And as long as that happens, we are inside of this delta ball. Everything else will stay exactly the same in our definition. We're just going to replace that one line, and I guess we'll replace where we're taking the limit. Everything else stays the same. So for a function f, which maps from R2 into R, we can say that the limit as xy approaches x naught y naught of f of x y is equal to L if and only if for all epsilon greater than 0 there exists delta greater than 0 such that the absolute value of f of x minus L is less than epsilon whenever 0 is less than the square root of x minus x naught squared plus y minus y naught squared is less than delta. Now, when we've worked with limits in the past, when we worked with limits for a function of a single variable, the one thing that we had to pay attention to was one-sided limits. Remember, we could say that the value of the limit was L if and only if the limit from the left and the limit from the right were the same thing. So if you think about our function and our arbitrary curve, the idea here was that you could trace the curve going this way, and you could trace the curve going that way, and we wanted to make sure we ended up at the same place. For a function of two variables, it's a little bit tricky because instead of just looking from the left and from the right, we can think about the paths that come downward like this. We can think about the paths that come over like this. We can think about paths that come in at an angle. We can think about paths that come in all squiggly in one way or another. Right? There are infinitely many different paths that we can take. And as long as all paths agree, then we're going to be good. The problem is all paths is quite a lot of paths. But here's where function composition can come in and be useful to us. If we have a function f of x and y, and we're trying to take the limit as x, y approaches x naught, y naught, we can establish some r of t which has r of c equals x naught, y naught, And then we can establish this as the limit as t goes to c of f of t. All right, so there is our path limit, and we can try to find as many paths as we want and make sure that they all match. Sometimes that's fairly straightforward to do. So for example, if I want to take the limit as xy approaches, say, 1, 2, for the function 7xy squared over x squared plus y squared. Well, because the properties of limits, or the definition of limits, looks so similar to the definition we've used before, it makes sense that we should be able to use the same tools that we've used before. So this limit should be the limit of the numerator divided by the limit of the denominator, provided that those things exist. If they don't exist, then we're going to end up with some trouble. So we plug in that x is equal to 1 and that y is equal to 2. We plug in that x is equal to 1 and y is equal to 2. And we get 7, 14, 28 over 5, which absolutely does exist. So in this case, we're good to go. We don't have to worry about anything else. If we look at something a little bit more tricky, then we start to run into some trouble. Say the limit as xy goes to 0, 0 of the function x squared minus y squared over x squared plus y squared. Well, if you try plugging in x equals 0 and y equals 0, you get 0 over 0, which we know is an indeterminate form. So one of the things we can try is looking at going through a couple of different paths. And if you can find two paths that disagree, you know you're done. But I'm going to set up three what I think are fairly obvious paths just so we can play around with it. Right? Our goal is to get to the point 0, 0. Some obvious paths you can take are going directly in along the x-axis, going directly in along the y-axis, or maybe going in at a 45-degree angle between them. All right, so we can look at three separate paths here and try to evaluate the function on each one. All right, let's name those R1, R2, and R3 just so we can start talking about this. Well, along path 1, f of 1, we put in x equals 0, we put in y equals t, we get negative t squared over t squared, which is negative 1 everywhere. Along f2, we get, well, t squared minus t squared is 0 over 2t squared, which is just 0 everywhere. And along our third path, we put in x equals t, y equals 0. We get t squared over t squared, which is just 1 everywhere. Right, so we should have to now look at the limit as t goes to 0 of f1, but that's just -1. We should look at the limit as t goes to 0 of f2, but that's just going to be 0. We should look at the limit as t goes to 0 of f3, but that's just going to be +1. Because these three limits do not agree with each other, the limit of the original function simply does not exist. To get some sense of what's happened here, once again, I've gone and I've graphed these curves. So we have the surface, f of x and y graphed. We have the curve along the x-axis, we have the curve along the y-axis, we have the curve along the line x equals y. If I look at this top down, swivel that around, maybe, come on, there we go. Now that looks like the xy plane. You can see that I have those three graphs put in parametrically. And if we swing that back around and the computer listens to me, you can see what's happening here, right? Um, every path going into that center point is going to take on a different value, just depending on the angle that you're going in. It's going to be somewhere between -1 and +1. It doesn't get any lower than that, doesn't get any higher than that, but yeah, depending on where you're looking along that slope, you're going to get a different path going in. Um, so you get very many different results coming out of this one. Right, so that's the picture of a limit which does not exist. And once we have a idea for a limit here, when limits are well behaved, things work nicely. When limits are poorly behaved, things work badly. But the title of this lesson was Limits and Continuity. So let's wrap up and look at continuity. And the definition of continuity is going to be exactly the same as what we've seen before. Words. Right? We say that our function f, which maps from R2 to R, is continuous at the point x naught, y naught, if and only if f of x naught, y naught is defined, the limit as xy approaches x naught, y naught of f of x and y exists, and the limit as xy approaches x naught, y naught of f of x and y is actually equal to f of x naught, y naught. It's the same definition of continuity that we've had for everything else, just looks a little bit different because it's a function of several variables. But we can use it in basically the same way. If the function is undefined, we know that the function is not continuous. If the function is defined, but we suspect something weird is happening, we can test this last point and determine if the function is actually continuous or not. So hopefully nothing too crazy happening here. Hopefully that all makes sense. It's the same vocabulary we've been dealing with before, just introducing an extra variable into the mix. We could do the same thing for a function of three variables. I'm not going to just for the sake of time. It's not something that we're going to really have the time to look at. So the jump from doing things for a function of one variable to doing the same thing for a function of two variables is pretty significant. Having just one variable simplifies things quite a bit. The jump from two variables to three variables is almost unnoticeably different. So once you understand how this works for two variables, 3, 4, or 27 variables works the same way. You know what you're doing. We don't have to go through it again. So I'm going to end off with a problem for you to try, as I often do. This time we're going to look at a function f of x and y equals 3x minus y squared over 2x plus y squared. And I would like you to figure out the limit as xy approaches 2, 3 of f of x and y. All right, I've gone horribly blurry again, so I apologize. But that's all the more I want you to look at here. Make sure that you understand the notation, make sure you understand the vocabulary, and that you're not panicking because it's a function of several variables now. But take a look at that, see what you come up with, and I'll see you in the next video.